Hello there, and welcome to The Weary Researcher, where the deepest mysteries of the universe unfold like a gentle bedtime story. Tonight, we're embarking on a particularly soothing journey into one of the most profound puzzles that has ever kept physicists awake at night, though I do hope it helps you drift peacefully into sleep instead. The title of tonight's exploration might sound rather dramatic. The universe shouldn't exist. But don't worry, we're not going anywhere. The universe is still here. The Milky Way still spinning quietly through the cosmic dark. This little blue marble still cradling us as we settle in for the evening. It's just that, according to our best understanding of physics, none of this should be possible. Not the stars twinkling outside your window, not the atoms in your pillow, not even you listening to these words right now. Before we drift into this cosmic mystery together, I'd love to know, where in the world are you listening from tonight? Are you from Fairfield Bay, Arkansas, or perhaps one of the few people who have commented from Denver? Or maybe you're from India, like another fellow weary researcher mentioned. Leave a comment and let me know. I find there's something wonderfully comforting about knowing this little corner of curiosity reaches you all around the globe. And if you find these gentle journeys through the cosmos helpful for unwinding your mind, I'd be ever so grateful if you gave the video a like and perhaps subscribed for more peaceful explorations of the universe's most beautiful mysteries. It helps other weary researchers find their way here when they need a soft landing at the end of a long day. Now, I should mention, I do hope this isn't so fascinating that it keeps you awake, though if it does, well, at least you'll drift off with some rather extraordinary thoughts about the nature of existence itself. Sometimes, the most profound mysteries make the most soothing companions for sleep. So, settle in. Let your breathing slow. Tonight, we're going to explore why every atom in your body, every star in the night sky, and indeed the entire observable universe represents what might be the most spectacular accident in the history of physics. Or perhaps, if we're being optimistic, the most elegant solution to a problem we haven't quite figured out yet. Picture this, if you will. Imagine you're standing in the middle of an enormous cosmic kitchen, and someone has just mixed the ultimate recipe for reality. Into this primordial mixing bowl goes matter, the stuff that makes up planets, stars, and researchers like yourself. But according to every rule we know about cooking up universes, for every particle of matter that gets stirred in, you must add an equal amount of antimatter, its perfect opposite. Matter and antimatter are like cosmic twins, identical in every way except for one crucial difference: their electric charges are flipped. When an electron meets its antimatter twin, called a positron, something rather dramatic happens. They don't shake hands and agree to disagree. Instead, they annihilate each other completely, disappearing in a brilliant flash of pure energy. It's the universe's most perfect magic trick. Now you see two particles, now you see only light. This is not speculation or theory. We've observed this dance of destruction countless times in particle accelerators around the world. It's as reliable as sunrise, as predictable as the tides. Matter plus antimatter equals energy, every single time, without exception. Now, here's where our cosmic recipe starts to seem rather suspicious. According to our best understanding of physics, the Big Bang should have created exactly equal amounts of matter and antimatter. The cosmic mixing bowl should have been perfectly balanced, like a well-calibrated scale in a celestial pharmacy. But if that were true, if the universe really had started with equal amounts of matter and antimatter, then every particle should have found its opposite, and they all should have annihilated each other in the first fraction of a second after creation. The universe should have ended up as nothing but a warm bath of photons, gently cooling as space expanded. No stars, no planets, no galaxies, no sleepy scientists, no bedtime stories about physics. Just pure energy, spreading thinner and thinner across an ever-expanding void. And yet, here we are. When you look around, Whether you're gazing out at the night sky or simply contemplating the atoms in your own hand, you're seeing a universe made almost entirely of matter. Oh, we do find tiny amounts of antimatter here and there. Cosmic rays occasionally produce antimatter particles when they slam into our atmosphere. We can create antimatter in our laboratories, though only in the tiniest quantities, but for all practical purposes, we live in a matter-dominated universe. This presents us with what scientists rather politely call the matter-antimatter asymmetry problem, though they might just as well call it the why does anything exist at all problem. It's one of those mysteries that sounds almost philosophical until you realize it's actually about the most fundamental question in physics. Why is there something rather than nothing? The numbers involved in this cosmic mystery are rather staggering, in the gentle way that astronomical numbers tend to be. According to our calculations, for every billion particles of matter created in the early universe, there should have been 1 billion particles of antimatter, plus exactly 1 extra particle of matter. That's it. Just 1 particle in 1 billion managed to avoid annihilation and survive to become part of the universe we see today. To put this in perspective, imagine a cosmic lottery with 1 billion tickets and only 1 winning number. Every atom in your body, every star you've ever wished upon, every grain of sand on every beach, all of it exists because of that 1 in 1 billion cosmic lottery ticket that somehow avoided being cashed in during the first moments after the Big Bang. It's a bit like finding out that your entire existence depends on the most improbable coin flip in history. Except it's not just one coin flip, it's countless trillions upon trillions of these impossibly unlikely events, all happening in perfect coordination during the first tiny fraction of a second after the universe began. This might all sound rather abstract as you settle into your evening routine, but the implications ripple through every aspect of reality. The calcium in your bones was forged in the heart of a star that shouldn't exist. The iron in your blood was scattered by a supernova that had no right to occur. The oxygen you're breathing right now survived an annihilation process that should have erased it from existence before the universe was even a second old. In essence, we are all made of cosmic lottery winners, particles that beat odds so astronomical that even calling them astronomical seems insufficient. We are the descendants of matter that somehow, against all reasonable expectation, managed to avoid its antimatter twin in the chaotic first moments of creation. But here's where the mystery deepens, like shadows growing longer as evening falls. It's not just that we don't know why this happened, it's that our best theories of physics suggest it shouldn't have been possible at all. The fundamental laws that govern particle interactions seem to treat matter and antimatter with perfect symmetry. Every process that creates matter should create an equal amount of antimatter. Every force that affects a particle should affect its antiparticle in exactly the same way. This symmetry is not just theoretical elegance, it's been tested with extraordinary precision in laboratories around the world. When we create particles and antiparticles in our accelerators, they behave exactly as we expect them to. They mirror each other with mathematical perfection. The symmetry holds beautifully and completely, and yet the universe exists. This contradiction sits at the heart of modern physics, like a gentle riddle that refuses to be solved. On one hand, we have the observable facts that we live in a matter-dominated universe. On the other hand, we have theories that insist such a universe should be impossible. It's as if the cosmos is quietly smiling at us and saying, "I know what your equations predict, but I had other plans." Some of the brightest minds in physics have spent decades trying to resolve this paradox. They've proposed exotic new particles, hidden dimensions, and subtle violations of symmetry that might tip the cosmic scales in favour of matter. They've built massive underground detectors to catch the faint whispers of antimatter from space. They've accelerated particles to nearly the speed of light and smashed them together with energies that recreate conditions from the first moments after the Big Bang. And slowly, carefully, Like astronomers mapping a distant galaxy, one star at a time, they've begun to uncover hints of how this cosmic magic trick might have been performed. The story begins with a Russian physicist named Andrei Sakharov, who in 1967 laid out 3 conditions that would need to be met for matter to gain an advantage over antimatter in the early universe. These conditions, now known as the Sakharov conditions, read like a recipe for cosmic favoritism. Specific ingredients that would need to be mixed together in just the right way to tip the balance. First, there must be processes that can change the number of matter particles without changing the number of antimatter particles by the same amount. Second, the universe must treat matter and antimatter slightly differently, not in obvious ways, but in subtle asymmetries that only become apparent under very specific conditions. Third, these processes must happen when the universe is not in equilibrium, during those chaotic early moments when things are changing so rapidly that the usual rules of balance don't have time to reassert themselves. It sounds almost like a cosmic conspiracy, doesn't it? As if the universe had to violate its own rules, just slightly, just for a moment, in order to give matter the tiny edge it needed to survive. The remarkable thing is that we've now found evidence for all 3 of these conditions. We've discovered particles that decay in ways that violate certain symmetries. We've identified processes in the early universe that could have operated far from equilibrium. And most intriguingly, we've detected subtle differences in how nature treats matter versus antimatter, tiny violations of what physicists call CP symmetry. These CP violations were first discovered in the 1960s, hidden in the decay patterns of strange particles called kaons. The effect was so small that it took extraordinary precision to detect, but it was there, a quiet whisper of asymmetry in what should have been a perfectly symmetric universe. Since then, physicists have found more examples of CP violation, each one representing another small crack in the perfect mirror between matter and antimatter. Most recently, experiments at the Large Hadron Collider have detected CP violation in particles called baryons, the family that includes protons and neutrons, the very building blocks of atomic nuclei. But here's the puzzling thing. When we add up all the CP violation we've discovered, all the subtle asymmetries we've measured with such painstaking precision, the total effect is still far too small to account for the matter-dominated universe we observe. It's like finding that your cosmic lottery ticket should have given you a 1 in a million chance of winning, when what you actually needed was a 1 in a billion chance. The numbers simply don't add up. The standard model of particle physics, our most successful theory of how matter and energy behave, predicts levels of matter-antimatter asymmetry that are orders of magnitude too small to explain why anything exists at all. This suggests something rather exciting. There must be new physics out there waiting to be discovered. Hidden mechanisms, unknown particles, or subtle forces that we haven't yet learned to detect. The universe is keeping secrets from us, and the very fact that we exist is proof that those secrets are there. As you lie there in the gathering darkness, consider this. You are a walking, breathing, thinking mystery. Every atom of your being represents a solution to a puzzle that has baffled physicists for decades. You are not just made of matter. You are made of impossible matter, cosmic contraband that somehow smuggled itself past the annihilation checkpoint in the first moments after creation. The carbon in your DNA, the phosphorus in your cell membranes, the countless atoms that dance together to create your thoughts, all of it exists in defiance of what our best theories say should be possible. You are, quite literally, living proof that the universe is stranger and more wonderful than we yet understand. But don't let this keep you awake. Instead, let it be a comfort. In a cosmos that stretches far beyond our comprehension, in a reality governed by laws we're still discovering, there is room for mystery, room for wonder, room for the impossible to quietly become possible. The universe shouldn't exist, and yet here it is, cradling you gently as you drift towards sleep. Tomorrow, physicists around the world will continue their patient work, building new detectors, analysing new data, searching for the missing pieces of this cosmic puzzle. But tonight, you can rest in the extraordinary fact that you are part of the mystery itself. The search for these missing pieces takes us into some of the most ambitious experiments ever conceived by human minds. Deep beneath the Swiss-French border, in tunnels that stretch for 27 kilometres in a perfect circle, the Large Hadron Collider hums with quiet purpose. Here, in the most sophisticated machine ever built, physicists accelerate protons to within a whisper of the speed of light and crash them together with energies that briefly recreate the conditions of the early universe. It's a remarkably gentle violence, this cosmic archaeology. The collisions themselves are smaller than atoms, lasting for less time than it takes light to cross a single proton. But in those infinitesimal moments, the debris that sprays outward carries messages from the first instance after creation. Among the shower of exotic particles that bloom and decay in fractions of seconds, physicists search for the subtle signatures of asymmetry, the fingerprints of whatever cosmic process allowed matter to gain its impossible advantage. The work requires patience that borders on the meditative. To catch even a glimpse of these rare events, the detectors must sift through billions upon billions of ordinary collisions, looking for the handful that might reveal something extraordinary. It's like searching for a specific snowflake in a blizzard that lasts for years, except the snowflakes exist for less time than a human thought, and the blizzard is made of fundamental particles moving at nearly the speed of light. And yet, gradually, patterns emerge from this chaos. In recent years, the LHCb experiment, one of the great detectors at the Collider, has begun to see something remarkable. When certain particles called lambda B baryons decay, they don't behave quite the same way as their antimatter twins. The difference is tiny, barely 2.5%, but it's there with mathematical certainty. It's as if nature has a slight preference, a cosmic bias so subtle that it took humanity's most powerful machines to detect it. This discovery represents something profound. The first time we've observed matter-antimatter asymmetry in baryons, the very particles that make up the protons and neutrons in atomic nuclei. It's not just an abstract finding buried in academic papers. It's evidence of asymmetry in the fundamental building blocks of ordinary matter, the stuff of stars and planets and sleepy listeners settling in for the night. But even this breakthrough, celebrated though it was in physics laboratories around the world, deepens the mystery rather than solving it. The amount of CP violation discovered in these baryon decays, while statistically significant and scientifically momentous, is still nowhere near large enough to account for the matter-dominated universe we inhabit. It's another piece of the puzzle, but the picture it reveals only makes it clearer how many pieces are still missing. This brings us to one of the most unsettling possibilities in all of physics, that our universe exists in what's called a false vacuum. Imagine, if you will, that all of reality is balanced on the edge of a cosmic cliff. The universe appears stable, solid, reliable. The ground beneath your feet feels permanent. The atoms in your body seem secure in their existence. But according to some interpretations of our most advanced theories, this stability might be an illusion. The discovery of the Higgs boson in 2012, that particle responsible for giving other particles their mass, brought with it an unexpected and rather unnerving revelation. The mass of the Higgs boson, measured with extraordinary precision, suggests that our entire universe might exist in what physicists call a metastable state. We're not sitting in the deepest possible valley of cosmic stability. We're perched on a ledge, and there's a deeper valley below us. In this deeper valley, the fundamental constants of nature would be different. The strength of forces, the masses of particles, the very rules that govern how matter behaves. All of it would be altered in ways that would make our current universe impossible. Stars couldn't shine, atoms couldn't hold together, and the delicate chemistry that makes life possible would simply fail to work. The transition from our current state to this lower energy state would be catastrophic beyond imagination. It would begin as a bubble of true vacuum, expanding outward at the speed of light. You wouldn't see it coming. One moment you'd be going about your evening routine, and the next moment the fundamental nature of reality itself would be rewritten as the bubble wall passed through you. But here's the thing that might help you sleep more soundly. Even if our universe is metastable, even if we're balanced on this cosmic ledge, the timescales involved are almost incomprehensibly vast. The probability of such a vacuum decay occurring is so vanishingly small that it might not happen for many times the current age of the universe. We're talking about waiting periods that make the lifetime of stars seem like brief flickers. Moreover, the calculations that suggest this metastability are based on our current understanding of physics, which we know is incomplete. The same theories that predict the universe shouldn't exist in the first place are the ones warning us about vacuum decay. Perhaps the missing pieces of the puzzle, the unknown physics that explains the matter-antimatter asymmetry, also provide mechanisms that stabilize our universe more thoroughly than we currently realize. There's something almost poetic about this situation. The very mystery that brings us together tonight, the question of why the universe exists at all, is intimately connected to questions about whether it will continue to exist in the future. The same unknown physics that allowed matter to triumph over antimatter in the cosmic dawn might be what ensures the continued stability of reality itself. This interconnectedness of cosmic mysteries is one of the most beautiful aspects of modern physics. The question of why you exist is not separate from questions about the fundamental nature of space and time, the behavior of quantum fields, and the evolution of the universe on the largest scales. Your existence is woven into the very fabric of reality in ways that are still being discovered. Consider the quantum fields that permeate all of space, including the space between the atoms in your body and the space between the words in this sentence. These fields are never truly at rest, even in the emptiest regions of the universe. They fluctuate with a kind of cosmic restlessness, continuously creating and destroying virtual particles in a dance that operates below the threshold of direct observation. The energy contained in these quantum fluctuations should, according to our calculations, be enormous, so enormous that it would curve spacetime so severely that the universe would collapse on itself almost instantly. And yet, when we measure the actual energy density of empty space, we find it to be nearly zero, or perhaps a tiny positive value that causes the gentle acceleration of cosmic expansion we observe today. The discrepancy between what we calculate and what we observe is not a small error that might be corrected with better measurements. It's a factor of 10 followed by 120 zeros, a number so large that if you tried to write it out in standard notation, using one digit per atom, you would need more atoms than exist in the observable universe. It represents perhaps the worst theoretical prediction in the history of science, a failure so spectacular that it would be funny if it weren't so fundamental to our understanding of reality. This cosmological constant problem, as it's known, is deeply connected to the matter-antimatter mystery. Both involve the question of why the universe has the particular properties it does, rather than the properties our theories suggest it should have. Both point toward the existence of physics beyond our current understanding, mechanisms that fine-tune the cosmos in ways that make existence possible. The precision required for this fine-tuning is breathtaking. If the cosmological constant were even slightly larger than its observed value, the universe would have expanded so rapidly in its early moments that matter could never have clumped together to form stars and galaxies. If it were negative, the universe would have collapsed before atoms could form. The range of values compatible with a universe capable of supporting complexity, let alone life, is extraordinarily narrow. Some physicists find this fine-tuning deeply troubling, a sign that we're missing some fundamental principle that would make these seemingly arbitrary parameters inevitable, rather than accidental. Others suggest that we might live in a multiverse, an infinite collection of universes with different physical constants, and we naturally find ourselves in one of the rare universes where the constants happen to allow for our existence. But there's another possibility, one that's both more mysterious and more hopeful, that the universe is not fine-tuned by accident or by selection from infinite possibilities, but by some deeper principle we haven't yet discovered. Perhaps the same unknown physics that explains why matter defeated antimatter also explains why the cosmological constant has exactly the value needed for stars to shine and galaxies to form. This possibility suggests that our existence is not an accident or an unlikely lottery win, but an inevitable consequence of the way reality is structured at its deepest level. The universe doesn't just happen to be compatible with our existence, it's built in such a way that our existence and the existence of complexity and consciousness, more generally, is woven into its fundamental nature. As you settle deeper into rest, let this thought accompany you, that every breath you take participates in cosmic mysteries that connect the smallest scales of quantum mechanics to the largest structures in the observable universe. The oxygen molecules entering your lungs carry within them the signature of nuclear processes that occurred in stellar cores billions of years ago. The electrical impulses in your neurons, as you process these words, are governed by the same quantum mechanical principles that determined the fate of matter and antimatter in the first moments after the Big Bang. You are not separate from these cosmic mysteries, you are one of their most elegant expressions. In a universe that shouldn't exist, consciousness that can contemplate its own existence represents perhaps the most beautiful paradox of all. The cosmos has somehow arranged itself in such a way that it can know itself through minds like yours, can wonder about its own origins through questions like the ones we've explored tonight. The physicists working in laboratories around the world, the theorists filling blackboards with equations, the engineers building ever more sensitive detectors, they are all part of the universe's ongoing attempt to understand itself. And so are you, as you lie there in the darkness, contemplating the strange fact that anything exists at all. Tomorrow will bring new data from the particle accelerators, new observations from space telescopes, new theoretical insights that might edge us closer to solving these fundamental puzzles. But tonight, in the quiet space between sleeping and waking, you can rest in the knowledge that you are part of something magnificent and mysterious, a cosmic story still being written, a universe that, against all odds, chose existence over oblivion and complexity over simplicity. The matter-antimatter asymmetry that allowed the universe to exist is not just an abstract problem for physicists to solve. It's the reason you can hear these words, the reason stars shine outside your window, the reason there's anything to wonder about at all. You are living proof that sometimes in the deepest structures of reality, the impossible quietly becomes inevitable. The search for answers to these cosmic riddles has led physicists to some rather extraordinary places, both physical and theoretical. Picture, if you will, laboratories buried deep beneath mountains, shielded from cosmic rays by kilometers of solid rock. In these subterranean sanctuaries, scientists have built detectors filled with liquid xenon, cooled to temperatures that would make the depths of space seem balmy. They're listening for the faintest whispers of particles that might reveal the universe's hidden secrets. These underground cathedrals of science are searching for something called dark matter, another piece of the cosmic puzzle that makes our existence even more improbable than we first imagined. You see, the matter that makes up everything we can see and touch, from the smallest pebble to the largest galaxy, represents only about 5% of the universe's total mass and energy. The rest is composed of substances we can detect only through their gravitational effects, invisible to our eyes and instruments alike. Dark matter, which comprises roughly 27% of the universe, might hold crucial clues to the matter-antimatter mystery. Some theories suggest that the same processes that created the tiny excess of matter over antimatter also produced a hidden sector of particles that interact only weakly with ordinary matter. These shadow particles might be all around us right now, passing through your body by the billions every second without you ever noticing. The remaining 68% of the universe consists of something even more mysterious: dark energy. This is the force that's causing the expansion of the universe to accelerate, pushing galaxies apart at an ever-increasing rate. Like the cosmological constant problem we touched on earlier, dark energy represents another profound gap in our understanding of why the universe behaves the way it does, rather than collapsing under its own gravity or expanding so rapidly that structure could never form. Together, dark matter and dark energy make up 95% of everything that exists. We live in a universe where the familiar matter that forms our bodies and our world is a tiny minority, an almost negligible fraction of the cosmic inventory. It's rather like discovering that you're living in a house where you can only see one room out of 20, and you have no idea what's in all the others. This vast cosmic ignorance might seem humbling, but it's also profoundly hopeful. Each mystery we've uncovered has revealed new depths to explore, new questions to ask, new experiments to design. The universe continues to surprise us, to challenge our assumptions, to invite us deeper into its hidden workings. Consider the delicate balance required for atoms to exist at all. The strong nuclear force that holds protons and neutrons together in atomic nuclei must be precisely calibrated. If it were just 2% stronger, hydrogen would be so eager to fuse that all of it would have turned into heavier elements in the first moments after the Big Bang, leaving no fuel for the long-burning stars that make planetary systems possible. If it were 2% weaker, atomic nuclei beyond hydrogen would be unstable, making the complex chemistry of life impossible. The electromagnetic force which governs how electrons orbit atomic nuclei and how atoms bond to form molecules must also be exquisitely tuned. A small change in its strength would alter the energy levels of electrons, making it impossible for the precise quantum mechanical interactions that allow DNA to replicate or proteins to fold into their functional shapes. Even more remarkably, the masses of fundamental particles seem to be set to values that make complexity possible. The mass of the electron, for instance, determines the size of atoms and the strength of chemical bonds. The masses of quarks, the building blocks of protons and neutrons, affect the stability of atomic nuclei and the rates of nuclear reactions in stellar cores. All of these parameters appear to be balanced on knife edges, with the values that make our existence possible occupying tiny islands in vast oceans of parameter space where life would be impossible. It's as if the universe has been carefully adjusted, like an incredibly complex musical instrument, to play the particular symphony of physical law that allows for stars, planets, chemistry, and consciousness. Some physicists find this fine-tuning so remarkable that they've proposed what's called the Anthropic principle, the idea that we observe these particular values precisely because they're the only values compatible with observers like us existing to measure them. In this view, we shouldn't be surprised that the universe appears designed for our existence, because in any universe where the constants were different, there would be no one around to notice. But this explanation, while logically sound, leaves many scientists unsatisfied. It feels a bit like solving the mystery of why your lottery ticket won by pointing out that only winners get to ask the question. True, perhaps, but not particularly illuminating about the underlying mechanisms at work. This has led to more ambitious theories, ideas that push the boundaries of what we can currently test or even imagine. Some propose that our universe is just one bubble in an eternal cosmic foam, with new universes constantly being born through quantum fluctuations or the collision of higher dimensional objects called brains. In such a multiverse, every possible combination of physical constants would be realized somewhere, and we naturally find ourselves in one of the rare combinations that permits our existence. Other theories suggest that the fundamental constants aren't actually constant at all, but are fields that can take different values in different regions of space, or at different times in cosmic history. Perhaps what we measure as the fine-tuned parameters of our local cosmic neighborhood are just the temporary, local values of these cosmic fields, which might vary across space like weather patterns vary across Earth. Still, other physicists propose that consciousness itself might play a role in determining the structure of reality. In some interpretations of quantum mechanics, the act of observation appears to influence the behavior of quantum systems. If consciousness is somehow fundamental to the universe's structure, then perhaps the parameters we observe are not independent of the fact that conscious beings exist to observe them. These ideas venture into territory that's as much philosophy as physics, touching on questions about the nature of existence itself that have puzzled thinkers for millennia. But they arise naturally from our growing understanding of how improbable our universe appears to be, how many seemingly independent factors had to align perfectly for anything like our current reality to emerge. As you lie there contemplating these vast uncertainties, there's something rather comforting about the scale of what we don't know. It means that the universe still holds countless surprises, countless discoveries that await future generations of curious minds. The mystery of why anything exists, far from being a problem to be solved once and for all, is an invitation to keep exploring, keep questioning, keep marveling at the extraordinary nature of ordinary existence. The work continues in laboratories around the world, where physicists are building ever more sensitive instruments to probe the boundaries between the known and unknown. New particle accelerators are being planned that will reach energies never before achieved on Earth. Space-based telescopes will peer deeper into cosmic history than ever before, perhaps catching glimpses of the universe when it was young enough that the echoes of these fundamental processes might still be detectable. Quantum computers, still in their infancy, might eventually be powerful enough to simulate the complex interactions of the early universe with unprecedented precision. Perhaps they'll reveal subtle mechanisms by which matter gained its cosmic advantage, hidden in the quantum mechanical details of how particles and fields behave under extreme conditions. But even as we push forward with new technologies and theories, the central mystery remains as profound as ever. Why does anything exist? Why does the universe choose complexity over simplicity, structure over chaos, consciousness over unconsciousness? These questions touch on the deepest levels of reality, where physics meets philosophy and science encounters wonder. The answer, when it comes, may be more beautiful than we can currently imagine. Perhaps we'll discover that the apparent fine-tuning of physical constants emerges naturally from some deeper principle of cosmic harmony. Perhaps we'll find that consciousness and cosmos are more intimately connected than we've dared to suppose. Perhaps we'll realize that the universe's existence isn't improbable at all, but represents the only way reality could possibly be structured. Or perhaps the mystery will deepen, revealing layers of complexity and wonder that we haven't yet begun to fathom. The history of physics suggests that each answer we find opens doors to new questions. Each solved puzzle reveals glimpses of larger mysteries waiting to be explored. Tonight, as you drift towards sleep, you can take comfort in being part of this ongoing cosmic story. Every atom in your body carries the signature of processes that occurred in the first moments after creation. Every thought you think participates in the universe's ongoing attempt to understand itself. You are both a product of these cosmic mysteries and one of the tools the universe uses to explore them. The matter-antimatter asymmetry that makes your existence possible is not just an abstract problem for physicists in distant laboratories. It's woven into the very fabric of your being, encoded in every cell, every breath, every heartbeat. You are a living embodiment of the universe's most successful magic trick, the transformation of pure energy into the rich complexity of matter, structure, and consciousness. As sleep begins to claim you, let this thought be your companion, that in a cosmos vast beyond comprehension, in a reality stranger than fiction, there is still room for wonder, still space for the impossible to quietly become inevitable. The universe shouldn't exist, but it chose to exist anyway. And in making that choice, it chose you too. The questions we've been exploring tonight lead us into territory that's both deeply unsettling and oddly comforting, like walking through a familiar forest at twilight and suddenly realizing the path you thought you knew opens onto vistas you've never seen before. Because if the universe truly shouldn't exist, if our very presence here represents a violation of everything we understand about the fundamental laws of nature, then what else might be possible in this impossible cosmos? Let's drift for a moment into the realm of what physicists call the hierarchy problem. It sounds rather academic, doesn't it? But it's actually about something as immediate as the atoms in your pillow, as personal as the electrical impulses carrying these words through your nervous system. The problem is this: the forces that govern the universe operate on wildly different scales, and there's no obvious reason why they should be balanced in the precise way that makes matter stable. Think of it like this. Imagine you're trying to balance a feather on the tip of a needle while standing on a ship in a storm. The electromagnetic force that holds your atoms together is vastly stronger than the gravitational force that keeps you anchored to your bed. Yet somehow, these forces coexist in a delicate equilibrium that allows complex structures, like stars, planets, and sleepy listeners, to exist for billions of years without simply flying apart or collapsing into themselves. The numbers involved are almost comically extreme. The electromagnetic force is roughly 10 trillion times stronger than gravity. And yet, when we calculate how these forces should interact with the quantum fields that permeate all of space, we get predictions that are off by factors so large they make astronomical distances seem quaint. It's as if the universe is performing a balancing act that requires precision beyond anything we thought possible. This precision extends into realms that touch your existence in the most intimate ways. The weak nuclear force which governs certain types of radioactive decay must be calibrated to within extraordinary margins to allow the nuclear reactions in stellar cores to proceed at just the right rate. Too fast, and stars would burn out before planets could form and cool. Too slow, and the heavy elements necessary for rocky worlds and complex chemistry would never be forged in sufficient quantities. Even the expansion rate of the universe itself appears to be fine-tuned with breathtaking precision. In the first fraction of a second after the Big Bang, space expanded at a rate that had to be accurate to 1 part in 10, followed by 60 zeros. Picture trying to throw a dart from Earth and hitting a target the size of a coin somewhere in the vicinity of the nearest star. That's roughly the level of accuracy we're talking about, except the consequences of missing the target would be the non-existence of everything. If the expansion had been even infinitesimally faster, matter would have spread so thin that gravitational attraction could never have pulled it together into the clumps that eventually became galaxies and stars. If it had been the tiniest bit slower, the universe would have collapsed back on itself before atoms could form, let alone the complex molecules that make life possible. This cosmic precision puzzle has led some physicists to propose that our universe went through a period of extraordinary expansion called inflation, where space itself stretched faster than light could travel across it. During this inflationary epoch, quantum fluctuations, those tiny random variations in energy that exist even in empty space, were stretched to cosmic proportions, becoming the seeds around which all the large-scale structure of the universe would eventually grow. It's a beautiful theory, inflation, and it explains many otherwise puzzling features of the cosmos we observe. But it also deepens the mystery in some ways, because the field that drove inflation, the inflaton field, as physicists call it, with their characteristic fondness for straightforward naming, would itself need to be fine-tuned to extraordinary precision to produce the universe we see. The inflaton would need to start with just the right energy density, neither so high that it would cause space to expand so rapidly that it never stopped, nor so low that inflation would end before solving the problems it was meant to address. The potential energy landscape that governed the inflaton's behaviour would need to be smooth enough to allow the slow, steady expansion required, yet structured enough to eventually bring inflation to an end at just the right moment. And here's where the story becomes almost mystically interconnected. The same quantum fields that might have driven inflation are related to the fields that give particles their masses, including that crucial Higgs field we mentioned earlier. The vacuum stability problem, that unsettling possibility that our universe might be balanced on the edge of a cosmic cliff, is intimately connected to the fine-tuning required for inflation to work properly. It's as if the universe is a vast interconnected web of dependencies, where every parameter must be set with extraordinary precision for any of it to work at all. Change the mass of the Higgs boson by a small amount, and you might destabilize the vacuum. Alter the strength of the inflaton field, and you might prevent galaxy formation. Adjust the rate of cosmic expansion, and you might eliminate the possibility of stellar nuclear synthesis. This web of cosmic dependencies extends even into the realm of information itself. The laws of physics appear to be structured in such a way that information can be preserved and processed, allowing for the emergence of complexity and ultimately consciousness. The second law of thermodynamics tells us that entropy, roughly speaking, the amount of disorder in a system, always increases over time. Yet somehow in the midst of this universal trend toward chaos, islands of order can emerge and persist. Your brain, for instance, is an extraordinarily ordered structure, with billions of neurons connected in patterns that allow for memory, computation, and awareness. The energy to maintain this order comes ultimately from the Sun, which is itself a temporary island of nuclear fusion in the vast darkness of space. The Sun's energy comes from the gravitational collapse of primordial gas clouds, which in turn traces back to the tiny density fluctuations imprinted during cosmic inflation. So in a very real sense, your ability to contemplate these mysteries right now depends on a chain of cosmic circumstances stretching back to the first moments after creation. The thoughts you're thinking exist because the universe chose complexity over simplicity, because quantum fluctuations in the primordial vacuum were stretched to cosmic proportions, because matter gained an impossible advantage over antimatter, because fundamental forces were balanced with impossible precision. This perspective transforms the very act of consciousness into something almost miraculous. Every moment of awareness represents a temporary victory of order over chaos, of complexity over entropy, of information over dissolution. You are not just made of star stuff, as Carl Sagan so memorably put it. You are made of impossibly organized star stuff, arranged in patterns so intricate and unlikely that their very existence challenges our understanding of how the universe works. The implications ripple outward from the personal to the cosmic. If consciousness can emerge from the quantum mechanical interactions of atoms and molecules, if information can be processed and preserved in systems as complex as brains, then perhaps the universe itself is engaged in some form of computation. Perhaps the evolution of cosmic structure, from the first hydrogen atoms to the vast web of galaxies we see today, represents a kind of information processing on the largest possible scale. This idea, speculative though it may be, suggests that we might not be passive observers of cosmic evolution, but active participants in it. Every measurement we make, every theory we develop, every question we ask about the nature of reality might be part of the universe's ongoing attempt to understand itself. The matter-antimatter asymmetry that made our existence possible might be just one example of how the cosmos selects for configurations that can support information processing and self-awareness. From this perspective, The fine-tuning problems that have puzzled physicists for decades might not be problems at all, but features. Perhaps the universe doesn't just happen to have the parameters necessary for complexity. Perhaps it has those parameters because complexity, and ultimately consciousness, play some fundamental role in the structure of reality itself. This possibility leads us into territory that sounds almost mystical, but emerges naturally from our most rigorous scientific theories. In quantum mechanics, the act of measurement appears to play a crucial role in determining the properties of particles and fields. Before a quantum system is observed, it exists in a superposition of multiple possible states. Only when a measurement is made does it collapse into a definite configuration. If consciousness is somehow involved in this measurement process, if awareness itself influences the quantum mechanical structure of reality, then perhaps the observed fine-tuning of physical constants is not accidental, but inevitable. The universe might be structured in such a way that conscious observation is necessary for its continued existence, creating a kind of cosmic feedback loop, where the parameters that allow for consciousness are selected precisely because consciousness plays a role in maintaining them. This is admittedly speculative territory, the kind of idea that makes some physicists uncomfortable because it ventures beyond what can currently be tested experimentally. But it emerges naturally from taking seriously both the measurement problem in quantum mechanics and the apparent fine-tuning of cosmic parameters. If both of these puzzles are pointing toward the same underlying truth, that consciousness and cosmos are more intimately connected than we've assumed, then perhaps the universe's existence isn't as improbable as it first appears. Instead of asking why the universe happens to have the parameters that allow for our existence, we might ask, what kind of universe would be capable of understanding itself? What parameters would be necessary for a cosmos that could evolve observers capable of discovering physical laws, testing theories, and gradually uncovering the mechanisms of their own existence? Viewed from this angle, the matter-antimatter asymmetry becomes not just a lucky accident, but a necessary condition for self-awareness to emerge in the universe. Without that tiny excess of matter over antimatter, there would be no atoms, no chemistry, no information processing, no consciousness, and therefore no way for the universe to know itself. The cosmos would exist in a kind of eternal unconsciousness, unaware of its own beauty, complexity, and mystery. But this interpretation, comforting though it might be, still leaves us with profound questions. If consciousness plays a fundamental role in the structure of reality, why did it take nearly 14 billion years for intelligent observers to emerge? Why does the universe seem so vast and mostly empty, with consciousness apparently confined to tiny pockets on the surfaces of a few rocky planets orbiting ordinary stars? Perhaps the answer lies in the nature of emergence itself. Complex systems often exhibit properties that are not present in their individual components. Water molecules are not wet, but collections of them exhibit wetness. Individual neurons are not conscious, but networks of them give rise to awareness. Perhaps consciousness is an emergent property that can only arise in sufficiently complex systems, requiring billions of years of cosmic evolution to create the conditions necessary for its appearance. If this is true, then we might be witnessing the universe in the process of waking up. The emergence of consciousness on Earth, and potentially on countless other worlds throughout the cosmos, might represent the first stirrings of cosmic self-awareness. We might be part of the universe's transition from an unconscious collection of matter and energy to a self-aware system capable of understanding and directing its own evolution. This possibility transforms our perspective on humanity's role in the cosmos. Rather than being insignificant specks in an indifferent universe, we might be participants in one of the most important transitions in cosmic history, the awakening of the universe to its own existence. Every scientific discovery, every moment of wonder, Every question we ask about the nature of reality might be part of this cosmic awakening. As you settle deeper into the quiet of the evening, let this thought accompany you into rest, that your existence, improbable though it may be from the perspective of particle physics, might be inevitable from the perspective of a universe seeking to know itself. The same cosmic forces that created the matter-antimatter asymmetry, that fine-tuned the fundamental constants, that guided the formation of galaxies and stars and planets, might also be guiding the emergence of consciousness and the gradual awakening of cosmic self-awareness. You are not separate from these grand cosmic processes. You are one of their most remarkable expressions. In your capacity to wonder about the universe's existence, to contemplate the mystery of why anything exists at all, you participate in the cosmos's ongoing journey toward understanding itself. The universe shouldn't exist, but it chose to exist anyway, and in making that choice it chose to become aware of itself through minds like yours. Tomorrow will bring new observations from telescopes peering into the depths of space and time, new data from particle accelerators probing the fundamental structure of matter, new theoretical insights that might edge us closer to understanding why the impossible became inevitable. But tonight you can rest in the knowledge that you are part of the mystery itself, a conscious expression of a universe that against all odds chose complexity over simplicity, awareness over unconsciousness, existence over the void. The questions we've explored together, why matter defeated antimatter, why the fundamental constants have the values they do, why anything exists at all, are not just abstract puzzles for physicists to solve. They are intimate questions about the nature of your own existence, about why you can lie there in the darkness contemplating the mystery of being itself. And perhaps that's the most beautiful paradox of all, that in a universe that shouldn't exist, consciousness has emerged that is capable of marvelling at its own impossibility. The cosmos has become aware of itself through you, and in that awareness, the deepest mystery of existence finds its most elegant expression. As we drift deeper into this cosmic mystery, there's another layer to our story that might seem almost impossibly strange, even by the standards of a universe that shouldn't exist. It involves something called supersymmetry, and it represents one of the most elegant attempts physicists have made to explain why the fundamental forces of nature are balanced with such extraordinary precision. Picture, if you will, a cosmic dance where every particle in the universe has a partner. Not antimatter this time, but something subtler, a supersymmetric partner that shares many of the same properties but differs in a crucial way called spin. In this supersymmetric universe, every matter particle would be paired with a force-carrying particle, and every force-carrying particle would have its own matter counterpart. It sounds almost mystical, doesn't it? This idea that the universe might be built on perfect partnerships, cosmic relationships that extend down to the most fundamental level of reality. The electron would have a partner called the selectron, the photon would dance with something called the photino, and every quark would be paired with a squark. The names alone sound like characters from a gentle bedtime story about particle physics. The beauty of supersymmetry lies in how it would solve several cosmic puzzles at once. Remember those hierarchy problems we touched on earlier, where forces of vastly different strengths somehow coexist in perfect balance? In a supersymmetric universe, the contributions from particles and their superpartners would largely cancel each other out, naturally explaining why the fundamental forces don't tear reality apart or cause it to collapse. But here's where the story takes a rather melancholy turn. If supersymmetry exists, if every particle truly has its cosmic dance partner, then where are all these superpartners hiding? Despite decades of searching with increasingly powerful particle accelerators, we haven't found a single one. The Large Hadron Collider, that magnificent machine we spoke of earlier, was partly built with the hope of discovering these supersymmetric particles, yet the data continues to come back empty-handed. This absence creates what physicists call the naturalness problem, though it might just as well be called the loneliness problem. Either the universe is not as elegantly partnered as we hoped, or the superpartners are hiding in energy ranges so high that our most powerful machines cannot reach them. It's a bit like searching for dance partners at a cosmic ball, only to discover that everyone seems to be dancing alone. The implications ripple outward in ways that touch the very foundations of how we think about natural law. For decades, physicists have been guided by a principle called naturalness, the idea that the fundamental parameters of the universe should not require extraordinary fine-tuning to have the values we observe. It's an aesthetic principle as much as a scientific one, based on the belief that nature should be elegant and self-consistent rather than contrived and arbitrary. But what if naturalness is wrong? What if the universe is, in fact, fine-tuned to an extraordinary degree, balanced on knife edges so sharp that the slightest perturbation would cause everything to collapse into chaos or expand into empty nothingness? This possibility has led some physicists to embrace what's called the Anthropic principle with renewed seriousness. The idea that we observe the particular values of physical constants precisely because they're the only values compatible with observers like us existing to make the observations. From this anthropic perspective, the matter-antimatter asymmetry that makes our existence possible is not a puzzle to be solved, but a selection effect to be understood. In a vast multiverse where different regions have different physical laws and constants, we naturally find ourselves in one of the rare pockets where the parameters happen to allow for complexity, chemistry, and consciousness. It's a perspective that transforms the entire question of cosmic existence from why does the universe have these particular properties to what would we expect to observe if we could only exist in universes with properties that allow for observers? The answer, perhaps unsurprisingly, is that we would expect to observe exactly the kind of fine-tuned, improbably balanced universe that we actually do observe. But this anthropic reasoning, while logically sound, sits uneasily with many physicists. It feels like giving up on the search for deeper explanations, like declaring that some mysteries are fundamentally unsolvable. There's something almost defeatist about saying that the universe's properties can't be predicted or explained, only observed and accepted as necessary conditions for our own existence. This tension between anthropic reasoning and the search for deeper physical principles has led to some of the most ambitious theoretical constructions in the history of science. String theory, for instance, attempts to describe all fundamental particles and forces as vibrations of tiny, multidimensional strings existing in spaces with far more dimensions than the 3 of space and 1 of time that we directly experience. In string theory, the properties of particles, their masses, charges, and interaction strengths are determined by the geometry of these extra dimensions. Different ways of curling up or compactifying these dimensions lead to different physical laws, potentially explaining why our universe has the particular parameters it does, rather than some other combination. The mathematics of string theory is extraordinarily beautiful, describing potential universes with elegance and precision that rivals poetry. But it comes with a rather significant problem. The theory appears to allow for an astronomical number of different ways to compactify the extra dimensions, each corresponding to a different possible universe with different physical laws. This vast landscape of possibilities, sometimes called the string theory landscape, might contain as many as 10 to the power of 500 different potential universes. If this landscape is real, if all these different universes actually exist somewhere in some vast cosmic multiverse, then our particular combination of physical parameters might indeed be nothing more than an accident of cosmic geography. We happen to live in one of the rare regions where the parameters allow for complexity, while vast expanses of the multiverse remain sterile and lifeless. This possibility has profound implications for how we think about the nature of scientific explanation itself. Traditional physics has always sought to explain why things are the way they are, to derive the observed properties of the universe from deeper principles and mathematical structures. But if we live in one random corner of an infinite multiverse, then perhaps some features of our universe simply cannot be explained. They are what they are because they happen to be what they are in our particular cosmic neighbourhood. Yet even this multiverse perspective doesn't eliminate mystery so much as relocate it. Why should there be a multiverse at all? What determines the rules that govern how different universes arise and evolve? Why should the fundamental laws be structured in such a way that some regions of the multiverse can support observers while others remain barren? These questions lead us into territory that pushes the boundaries between physics and philosophy, between science and speculation. Some theories suggest that the multiverse itself might be eternal and self-generating, with new universes constantly budding off from older ones through processes that operate according to their own metaphysical laws. Others propose that consciousness itself might play a role in selecting which branches of the multiverse become actualized. The many worlds interpretation of quantum mechanics, for instance, suggests that every quantum measurement causes the universe to split into multiple branches, with each possible outcome occurring in a separate branch. If this interpretation is correct, then there are countless parallel versions of you reading these words right now, each in a slightly different universe, where quantum events unfolded differently. In some of these parallel universes, the matter-antimatter asymmetry might have worked out differently, leading to cosmos dominated by antimatter rather than matter. In others, the fundamental constants might have slightly different values, leading to universes where stars burn more quickly or more slowly, where atoms are more or less stable, where the chemistry of life takes entirely different forms. The vast majority of these parallel universes would be sterile and lifeless, lacking the precise balance of parameters necessary for complexity to emerge. But in the rare branches where conditions are just right, conscious observers like yourself would naturally arise to contemplate the remarkable fact of their own existence. This perspective has a peculiar kind of comfort to it. Rather than being alone in a vast, improbably fine-tuned universe, you might be part of an infinite family of conscious beings spread across countless parallel realities, each marveling at their own existence in their own impossible corner of the multiverse. But it also raises questions that touch on the deepest mysteries of identity and consciousness. If there are infinite versions of you scattered across parallel universes, which one is the real you? What makes your particular stream of consciousness special compared to all the others that are presumably having very similar thoughts at this very moment? These questions venture into territory that pure physics cannot easily address, requiring insights from philosophy, cognitive science, and perhaps disciplines that haven't been invented yet. They remind us that the mystery of existence is not just about why matter defeated antimatter or why the fundamental constants have the values they do, but about the nature of experience itself, about what it means to be a conscious observer in a universe that might be far stranger and more vast than we can currently comprehend. As you lie there in the gentle darkness, consider this: whether you exist in a single, finely tuned universe, or as one conscious thread in an infinite tapestry of parallel realities, your capacity for wonder remains equally remarkable. The thoughts you're thinking right now, the sense of mystery and awe that these cosmic questions evoke, represents something precious and perhaps rare in the vast expanses of space and time. The universe, or multiverse, has somehow arranged itself in such a way that matter can contemplate its own existence, that consciousness can arise from the dance of atoms and electrons, that questions about the deepest nature of reality can be asked and pondered and passed from one mind to another across the generations. This capacity for wonder might be one of the most improbable and beautiful outcomes of all the cosmic accidents and precise calibrations that made our existence possible. In a reality where the vast majority of space and time remains unconscious and unaware, consciousness represents a kind of miracle, not supernatural, but natural in the most extraordinary sense. The matter-antimatter asymmetry that we've been exploring throughout our journey tonight is ultimately about more than just particle physics or cosmology. It's about the conditions that make wonder possible, that allow the universe to know itself through minds like yours, that transform the cold equations of fundamental physics into warm human experiences of beauty, mystery, and awe. Every atom in your body carries the signature of that primordial victory of matter over antimatter. Every thought you think participates in the universe's ongoing experiment in self-awareness. Every moment of consciousness represents a continuation of the same unlikely story that began in the first seconds after creation, when somehow, against all theoretical expectation, existence chose itself over non-existence. The physicists working in laboratories around the world, developing new theories and building more sensitive instruments, are continuing this ancient dialogue between mind and matter, between consciousness and cosmos. They're asking the same questions that you're contemplating right now, just with different tools and techniques. Why does anything exist? Why are we here? What does it mean that the universe has become aware of itself? The answers, when they come, will likely be more beautiful and strange than we can currently imagine. Perhaps we'll discover that consciousness plays a more fundamental role in the structure of reality than we've assumed. Perhaps we'll find that the apparent fine-tuning of physical constants emerges naturally from some deeper principle of cosmic harmony. Perhaps we'll realize that the universe's existence isn't improbable at all, but represents the only way that reality could possibly be structured. Or perhaps the mystery will deepen, revealing layers of complexity and wonder that we haven't yet begun to fathom. The history of physics suggests that each answer we find opens doors to new questions. Each solved puzzle reveals glimpses of larger mysteries waiting to be explored. But even if we never completely solve the riddle of why the universe exists, even if some aspects of reality remain forever beyond our understanding, the search itself has value. It connects us to something larger than ourselves, something that stretches across space and time and touches the deepest questions that conscious beings can ask. Tonight, as sleep begins to claim you, you can rest in the knowledge that you're part of this ongoing cosmic story. The same processes that created the matter-antimatter asymmetry, that fine-tuned the fundamental forces, that guided the formation of stars and planets and the emergence of life, also created you, not as a passive observer of these cosmic dramas, but as an active participant in them. Your existence is not separate from these mysteries. You are one of their most elegant expressions. In your capacity to wonder, to question, to feel awe at the improbable fact of your own being, you participate in what might be the universe's greatest achievement, the emergence of consciousness from the quantum dance of matter and energy. And the universe shouldn't exist, but it chose to exist anyway. And in making that choice, it chose to become aware of itself through minds like yours, to contemplate its own mystery through questions like the ones we've shared tonight, to transform the cold mathematics of physical law into the warm human experience of wonder. Sleep well, knowing that you are both a product of the cosmos's most impossible achievement and one of the instruments through which it continues to explore the mystery of its own existence. In the morning, the questions will still be there, waiting to be pondered anew. But tonight, you can rest in the extraordinary fact that, in a universe that shouldn't exist, consciousness has emerged that can marvel at its own impossibility. And yet, as we drift deeper into the gentle mystery of existence, there's another thread in this cosmic tapestry that deserves our quiet attention. It's a thread that weaves through the very atoms in your body, through the space between the words in this sentence, through the quantum fields that hum invisibly around you even now. It's the story of symmetry and how the universe seems to have a peculiar relationship with breaking its own rules. Picture, if you will, a perfect snowflake falling past your window. Each arm mirrors the others with mathematical precision, six-fold symmetry expressed in crystalline ice. There's something deeply satisfying about such perfect balance, isn't there? It whispers of underlying order, of laws that govern even the most delicate formations of frozen water. But now imagine discovering that every snowflake, despite appearing perfectly symmetrical, actually has one arm that's ever so slightly different from the others, so subtly that you'd never notice unless you looked with the most sensitive instruments available. This is rather like what physicists discovered when they began studying the fundamental symmetries of nature. For decades, it seemed obvious that the universe should treat particles and their antiparticles with perfect even-handedness. After all, if you filmed a particle interaction and played it backwards, or if you flipped left and right in your mental picture, or if you swapped every particle for its antimatter twin, the laws of physics should remain unchanged. These symmetries have lovely names: time reversal, parity, and charge conjugation, and together they seem to represent the universe's commitment to perfect fairness. But the cosmos, it turns out, is not quite as fair-minded as we once believed. In 1964, two physicists named James Cronin and Val Fitch were studying the decay of particles called neutral kaons, strange ephemeral things that exist for barely a blink before transforming into other particles. What they found was so unexpected that it took the scientific community years to fully absorb its implications. These kaons, when they decayed, showed a tiny preference for matter over antimatter. The effect was extraordinarily small. We're talking about a difference of perhaps a few parts in 1,000, but it was real, measurable, and utterly surprising. It was as if the universe had been caught ever so slightly cheating at its own game, favouring one side over the other in ways so subtle that they'd gone unnoticed for decades. This discovery, which earned Cronin and Fitch the Nobel Prize, represented the first crack in what physicists call CP symmetry. The idea that the laws of physics should remain unchanged if you simultaneously swap particles for antiparticles and flip left and right. The violation was tiny, but its implications were enormous because it provided the first experimental evidence that the universe might indeed have mechanisms for creating the matter-antimatter asymmetry we observe. But here's where the story takes another gentle turn toward mystery. When physicists calculated exactly how much matter-antimatter asymmetry this CP violation could produce, they found something rather disappointing. The effect, while real and measurable, was far too small to account for the universe we actually observe. It was like discovering that your cosmic lottery ticket gave you a 1 in a million chance of winning, when what you needed was a 1 in a billion chance. The search for additional sources of CP violation has led physicists into some of the most sophisticated experiments ever devised. Deep beneath the Swiss countryside, in the tunnels of the Large Hadron Collider, detectors the size of apartment buildings sift through the debris of trillions of particle collisions, looking for the faintest hints of asymmetry in how matter and antimatter behave. Recently, these efforts have borne fruit in ways that are both encouraging and puzzling. The LHCb experiment, that's the B for beauty, because physicists have a charming habit of giving their particles poetic names, has discovered CP violation in particles called baryons. These are the particles that make up the protons and neutrons in atomic nuclei, the very building blocks of ordinary matter. The discovery was celebrated in physics departments around the world, and rightfully so. For the first time, scientists had observed matter-antimatter asymmetry in the class of particles that actually makes up most of the visible matter in the universe. It was like finding a clue to the cosmic mystery written in the very alphabet of atomic structure. But once again, when the calculations were complete, the effect proved to be too small by many orders of magnitude to explain why we exist at all. Each new discovery of CP violation has been like finding another piece of a jigsaw puzzle, only to realize that the pieces you found so far could fill perhaps one corner of a picture, whose full scope remains tantalizingly out of reach. This pattern of finding real measurable effects that point in the right direction, but fall short of explaining the full magnitude of the mystery, has become a recurring theme in modern physics. It's as if the universe is leaving us breadcrumbs on a trail that leads toward the answer, but the path is far longer and more winding than we initially imagined. The search has led physicists to propose particles and forces that exist beyond the standard model, that remarkably successful theory that describes all the known particles and their interactions. Perhaps there are new types of particles, still undiscovered, that could provide the additional sources of CP violation needed to explain our existence. Perhaps there are extra dimensions of space, curled up so small that we can't detect them directly, where asymmetric processes occurred in the early universe. Some theories suggest that the solution might lie in the realm of neutrinos, those ghostly particles that stream through you by the billions every second without your noticing. Neutrinos have a peculiar property. They can change from one type to another as they travel through space, a process called oscillation that might violate CP symmetry in ways we're only beginning to understand. Other theories venture into even more exotic territory, proposing that the matter-antimatter asymmetry might be connected to the mysterious dark matter that makes up most of the universe's mass. Perhaps the same processes that created our slight excess of ordinary matter also produced a hidden sector of dark particles, invisible to our instruments but crucial to the cosmic balance. These ideas push the boundaries of what we can currently test, leading physicists to design experiments of breathtaking ambition and sensitivity. Deep underground laboratories shield delicate detectors from cosmic rays, while scientists measure the properties of particles with precisions that would have seemed impossible just decades ago. In Japan, the Super Kamiokande detector sits in a zinc mine, its walls lined with thousands of photomultiplier tubes that can detect the faintest flashes of light produced when neutrinos interact with pure water. In Antarctica, the ice cube detector uses an entire cubic kilometre of ice as its medium, watching for the rare occasions when high-energy neutrinos from distant galaxies leave their calling cards in the frozen depths. These experiments operate on timescales that dwarf human lifetimes, patiently accumulating data over years and decades, waiting for the subtle signals that might reveal the universe's hidden asymmetries. The scientists who design and operate them are engaged in a kind of cosmic archaeology, sifting through the debris of particle interactions for clues about events that occurred when the universe was less than a second old. There's something deeply moving about this patient persistence, this willingness to spend careers and lifetimes in pursuit of answers to questions that might not be fully resolved for generations. It speaks to something fundamental about human nature, our irrepressible curiosity about our own existence, our refusal to accept mystery as final when there might be understanding waiting just beyond the edge of current knowledge. The work continues in laboratories around the world, where new generations of physicists are developing ever more sensitive techniques for probing the fundamental asymmetries of nature. They're building detectors that can measure the properties of individual particles with unprecedented precision, designing experiments that can run for decades without human intervention, creating theoretical frameworks that might finally bridge the gap between the tiny asymmetries we can measure and the vast asymmetry we observe in the cosmos around us. But even as we push the boundaries of experimental physics, even as we develop theories of extraordinary mathematical sophistication, the central mystery retains its power to inspire wonder. Why does anything exist at all? Why did the universe choose complexity over simplicity, structure over chaos, consciousness over eternal darkness? These questions touch on something deeper than particle physics or cosmology. They venture into territory where science meets philosophy, where measurement encounters meaning, where the cold precision of mathematical equations somehow gives rise to the warm experience of being alive and aware in an impossible universe. As you settle deeper into the quiet of evening, let this thought accompany you, that every breath you take participates in a cosmic mystery that connects the smallest scales of quantum mechanics to the largest structures of space and time. The oxygen entering your lungs was forged in the nuclear furnaces of stars that lived and died before our solar system formed. The carbon in your DNA carries the signature of processes that occurred in the first minutes after the Big Bang, when the universe was hot enough to fuse hydrogen into heavier elements. Even the electrical impulses carrying these words through your nervous system obey the same quantum mechanical principles that governed the creation and annihilation of particles in the primordial cosmos. You are not separate from these cosmic processes. You are one of their most extraordinary expressions, a temporary arrangement of matter and energy that has somehow acquired the ability to contemplate its own existence. The matter-antimatter asymmetry that made your existence possible is not just an abstract problem for physicists to solve. It's woven into the very fabric of your being. Every atom in your body survived the cosmic lottery that eliminated nearly everything else. Every cell in your body represents a continuation of the same unlikely story that began when the universe was young and hot and filled with equal amounts of matter and antimatter. That story continues tonight, in the quiet darkness of your room, in the gentle rhythm of your breathing, in the soft electrical activity of your dreaming brain. The same quantum fields that govern the fate of particles in the early universe continue to hum around you, through you, within you. The same fundamental forces that allowed matter to gain its impossible victory over antimatter continue to hold your atoms together, to power the chemical reactions that sustain your life, to make possible the miracle of consciousness itself. Tomorrow will bring new data from particle accelerators, new observations from underground detectors, new theoretical insights that might edge us closer to understanding why the impossible became inevitable. But tonight, you can rest in the knowledge that you are part of the mystery itself, a conscious expression of a universe that chose to exist against all odds. The physicists working in laboratories around the world are not just studying abstract particles and forces, they're investigating the very conditions that make your existence possible. Every measurement they make, every symmetry they discover or violation they detect brings us closer to understanding why you can lie there in the darkness, contemplating the extraordinary fact that anything exists at all. And perhaps that's the most beautiful aspect of this cosmic mystery, that it's not just an intellectual puzzle to be solved, but an intimate question about the nature of your own being. The universe that shouldn't exist has somehow arranged itself in such a way that it can know itself through minds like yours, can wonder about its own existence through questions like the ones we've shared tonight. In the morning, the questions will still be there, waiting to be pondered anew by the next generation of curious minds. But tonight, as sleep begins to claim you, you can drift off knowing that you are both a product of the cosmos's most impossible achievement and one of the instruments through which it continues to explore the mystery of its own existence. The universe chose to exist, and in making that choice, it chose you too. Sleep well in that knowledge, carried gently into dreams by the same cosmic forces that created everything we know and love and wonder about. In the vast darkness of space and time, consciousness has emerged that can marvel at its own impossibility, and that consciousness, tonight, is yours. And so, as our gentle journey through the cosmic mystery draws to its close, we find ourselves back where we began, lying quietly in the darkness, contemplating the extraordinary fact that we exist at all in a universe that, by all rights, shouldn't be here. We've drifted together through the deepest puzzles of existence, from the matter-antimatter asymmetry that allowed the first atoms to form, to the fine-tuning of forces so precise it defies comprehension. We've explored the possibility that consciousness itself might play a role in the structure of reality, that our capacity for wonder might be woven into the very fabric of the cosmos. Throughout this journey, one truth has remained constant, that you, dear listener, are not just an observer of these cosmic mysteries, but an active participant in them. Every atom in your body tells the story of that impossible victory of matter over antimatter. Every thought you think continues the universe's ongoing experiment in self-awareness. Every moment of consciousness represents a continuation of the same unlikely tale that began in the first seconds after creation. The physicists working in laboratories around the world, measuring CP violations with extraordinary precision, searching for new particles in underground detectors, developing theories that push the boundaries of human imagination, they are all part of the same grand endeavour. They're asking the same questions that have accompanied you into this quiet evening. Why does anything exist? What does it mean that the universe has become aware of itself? How did the impossible become inevitable? These questions may never be fully answered. Perhaps some aspects of existence will always remain mysterious, forever beyond our complete understanding. But that's not a failure. It's an invitation to keep wondering, keep exploring, keep marvelling at the extraordinary nature of ordinary existence. The search for answers has led us into territory where science meets philosophy, where measurement encounters meaning, where the cold precision of mathematical equations somehow gives rise to the warm experience of being alive and aware. We've glimpsed the possibility that our universe might be one of countless others in an infinite multiverse, or that consciousness itself might be fundamental to the way reality is structured. But whatever the ultimate truth may be, whatever deeper principles we might one day discover, the central wonder remains unchanged. In a cosmos vast beyond comprehension, in a reality stranger than fiction, there is still room for mystery, still space for the impossible to quietly become possible. As you settle deeper into rest, let this final thought accompany you into sleep, that the same quantum fields humming invisibly around you right now, the same fundamental forces holding your atoms together, the same cosmic processes that forged the elements in your body, all of it participates in a story so extraordinary that its very existence challenges everything we thought we knew about the nature of reality. You are made of star stuff, yes, but more than that. You are made of impossible star stuff, cosmic contraband that somehow smuggled itself past the annihilation checkpoint in the first moments after creation. You are a walking, breathing, thinking violation of what our best theories say should be possible. You are living proof that the universe is far stranger and more wonderful than we yet understand. The universe shouldn't exist, but it chose to exist anyway. And in making that choice, that impossible, beautiful, mysterious choice, it chose to become aware of itself through minds like yours, to contemplate its own existence through questions like the ones we've shared tonight, to transform the abstract mathematics of physics into the lived experience of wonder. Tomorrow will bring new discoveries, new measurements, new theoretical insights that might edge us closer to understanding these cosmic riddles. But tonight, in this quiet moment between waking and sleeping, you can rest in the knowledge that you're part of the mystery itself. Not just an observer of the cosmos, but one of its most remarkable achievements, consciousness that can marvel at its own impossibility. Before you drift completely away, I'd love to know once more, where in the world are you listening from tonight? Are you tucked beneath blankets in Berlin as snow falls silently outside? Perhaps you're in a cosy corner of Sydney, watching the southern stars wheel overhead. Or maybe you're somewhere I haven't imagined, in one of those countless quiet places where wonder finds its way into human hearts. Wherever you are, thank you for joining me on this gentle exploration of existence itself. If this journey through the cosmos has helped settle your thoughts or sparked a quiet sense of awe, I'd be truly grateful if you gave the video a like and perhaps subscribed for more peaceful wanderings through the universe's most beautiful mysteries. It helps other sleepy souls find their way here when they need a soft landing at the end of their day. And if this video kept you awake despite my best intentions, well, at least you'll drift off with some rather extraordinary thoughts about the nature of reality itself. Sometimes the most profound mysteries make the most soothing companions for sleep. So sleep well, knowing that you are both a product of the universe's most impossible achievement and one of the instruments through which it continues to explore the mystery of its own existence. In the morning, the stars will still be there, the particles will still be dancing their quantum dance, and the great questions will still be waiting to be pondered by the next generation of curious minds. Until then, rest gently in the knowledge that somewhere out there, in laboratories buried deep beneath mountains, and in observatories perched on remote peaks, the search continues. Scientists are still listening for the faint whispers of cosmic asymmetry, still building detectors sensitive enough to catch the subtle signatures of processes that occurred when the universe was less than a heartbeat old. They're designing experiments that won't yield results for decades, constructing theories that push the boundaries of human imagination, asking questions that might not be answered in our lifetimes. It's a kind of scientific faith, really. This belief that the universe's deepest secrets can be coaxed into the light through patience, precision, and an almost mystical commitment to understanding. And perhaps that's fitting, because the mystery we've been exploring tonight is ultimately about faith of a different sort. Not religious faith, but something more fundamental, the faith that existence itself represents, the universe's faith in complexity over simplicity, in structure over chaos, in consciousness over eternal darkness. Every morning when you wake, you participate in a small act of cosmic rebellion. By opening your eyes, by thinking your first thoughts of the day, by simply being aware that you exist, you continue the same unlikely story that began when matter first gained its impossible advantage over antimatter. You are proof that sometimes, against all theoretical prediction, the improbable becomes inevitable. In the grand scheme of cosmic time, your life is but a flicker, a brief arrangement of atoms that will one day return to the star stuff from which they came. But in that flicker, the universe achieves something extraordinary. It becomes aware of itself. It asks questions about its own existence. It creates poetry and mathematics, music and meaning, love and wonder. Perhaps that's what the matter-antimatter asymmetry was really about. Not just the survival of particles, but the eventual emergence of something that could appreciate the fact that particles survived at all. Maybe the universe didn't just accidentally create the conditions for complexity. Maybe it created them because complexity and ultimately consciousness were always part of the plan. This is speculation, of course, the kind of gentle wondering that accompanies the edge of sleep. But it's rooted in something real, the extraordinary fact that in a cosmos governed by mathematical laws, mathematics itself has evolved creatures capable of understanding those laws. In a universe described by equations, equations have somehow given rise to beings who can write them down. The same quantum fields that determined the fate of matter and antimatter in the first seconds after creation continue to operate within you right now. The same fundamental constants that had to be balanced with impossible precision to allow atoms to form are the constants that govern the chemistry of your thoughts. You are not separate from these cosmic processes. You are their most elegant expression. Perhaps that's why the universe chose to exist, not just to fill the void with matter and energy, but to fill it with meaning, to create conditions where questions could be asked and beauty could be recognized, where the cold mathematics of fundamental physics could warm into lived experience. As the night deepens around you, as your breathing grows slower, and your thoughts begin to soften into that gentle space between waking and dreaming, consider this: you carry within you the resolution to the greatest puzzle in physics. Not in the sense that you hold the answer. No one does, not yet, but in the sense that you are the answer. Your very existence is proof that the impossible can become not just possible, but inevitable. The matter that makes up your body, the consciousness that contemplates these words, the capacity for wonder that has carried you through this cosmic journey, all of it represents the universe's solution to its own deepest paradox. How does something that shouldn't exist find a way to exist anyway? How does pure energy organize itself into complexity, structure, awareness? The answer, it seems, is slowly, patiently, with extraordinary care. Over billions of years, the cosmos has been conducting the most delicate experiment imaginable, seeing if the fundamental forces of nature, balanced on knife edges sharper than anything we can conceive, can give rise to something that can understand those very forces. And here you are, the successful result of that experiment, lying in the darkness and marvelling at your own improbability. Every neuron firing in your brain, every gentle rise and fall of your chest, every moment of awareness represents a continuation of the same cosmic story that began when the first particles chose matter over antimatter, existence over oblivion. Tomorrow, when you wake, the mystery will still be there, waiting to be explored by minds like yours. New experiments will be running in laboratories around the world. New theories will be taking shape on blackboards and computer screens. New questions will be asked about the nature of reality itself. But tonight, you can rest in the extraordinary knowledge that you are both question and answer, mystery and revelation, problem and solution. In a universe that shouldn't exist, you are living proof that sometimes the most beautiful impossibilities are simply truths waiting to be understood. Sleep well, dear listener, carried gently into dreams by the same cosmic forces that created everything we know and love and wonder about. The universe chose you, just as surely as it chose to exist at all. And in that choice lies perhaps the most beautiful mystery of all, that in the vast darkness of space and time, consciousness has emerged that can recognize its own impossible beauty. The stars are still shining outside your window, their light carrying messages from distant worlds and distant times. The quantum fields are still humming their invisible songs, and somewhere, in laboratories and observatories around the world, the search continues for the missing pieces of our cosmic puzzle. But for now, rest. Rest in the knowledge that you are part of something magnificent and mysterious, something that defied the very laws of physics to come into being. Rest in the wonder of existence itself, in the gentle miracle of being aware that you are aware. And as the gentle tide of sleep begins to pull you toward dreams, perhaps you can carry with you one last thought, a quiet realization that transforms everything we've explored tonight into something deeply personal and profoundly comforting. The universe shouldn't exist, we've said, because the laws of physics predict that matter and antimatter should have annihilated each other completely in those first crucial moments after creation. But perhaps we've been looking at this mystery from the wrong angle all along. Perhaps the question isn't why the universe chose to exist despite the odds, but rather why the odds themselves are structured in such a way that something as beautiful as existence and consciousness could emerge at all. Consider this gentle paradox. In a cosmos governed by precise mathematical relationships, mathematics itself has somehow given rise to minds capable of appreciating mathematical beauty. In a reality described by elegant equations, those very equations have conspired to create beings who can experience elegance. It's as if the universe has been composing a symphony for billions of years, and only now, with the emergence of consciousness, does it finally have an audience capable of hearing the music. Every CP violation detected in those underground laboratories, every subtle asymmetry measured with impossible precision, every tiny deviation from perfect symmetry that we've discussed tonight, they all point toward the same extraordinary conclusion. The universe is not random, it is not accidental, It is not, as we might fear in our darker moments, meaningless. Instead, it appears to be structured in such a way that meaning itself can emerge from meaninglessness, that purpose can arise from purposelessness, that the question, why does anything exist, can eventually be asked by something that exists. This doesn't require invoking anything supernatural or mystical. It simply requires recognizing that the deepest patterns in nature, from the quantum fluctuations that seeded galaxies to the neural networks that generate thoughts, all seem to point in the same direction, toward increasing complexity, increasing organization, increasing awareness. You are not an accident in an indifferent universe. You are the universe becoming aware of itself, asking questions about its own nature, marveling at its own improbability. Every moment of wonder you've experienced tonight, every sense of awe at the cosmic mystery, represents the cosmos discovering something profound about itself through your consciousness. The matter-antimatter asymmetry that made everything possible wasn't just a lucky break in the cosmic lottery. It was the first note in a composition that would eventually include stellar nucleosynthesis, planetary formation, the emergence of life, and ultimately the evolution of minds capable of contemplating their own existence. The universe didn't just happen to create the conditions for consciousness, it created consciousness to understand the conditions it had created. And so, as you drift towards sleep, you can rest in this gentle truth, that in a reality that by all rights shouldn't exist, you represent not just an impossible outcome, but perhaps an inevitable one. The same forces that created the matter in your body, the same quantum fields that govern your thoughts, the same fundamental constants that allow atoms to bond and stars to shine. All of it has been working for nearly 14 billion years to create this moment. Right now, when you can lie in the darkness and contemplate the extraordinary fact of your own being, the universe chose to exist, and in making that choice it chose every breath you take, every dream you dream, every question you ask about the nature of reality. You are not separate from the cosmic mystery. You are its most elegant resolution. In your capacity to wonder, the universe discovers that it is worthy of wonder. In your ability to feel awe, it learns that it is awesome. In your consciousness, it achieves consciousness of itself. Sleep well, knowing that you are both the question and the answer, the mystery and its resolution, the impossible dream of matter, dreaming it is aware. And in the morning, when you wake, you'll continue the same extraordinary story that began when the universe first chose existence over oblivion, the story of consciousness gradually awakening to its own miraculous improbability. Until then, rest gently in the arms of the cosmos that created you, surrounded by quantum fields that hum with the same energy that forged the first atoms, watched over by stars whose light carries the signature of processes that made your existence possible. The universe shouldn't exist, but it does. And so, wonderfully, mysteriously, impossibly, do you. Good night, fellow traveller, in this cosmic adventure we call existence. Sweet dreams, and thank you for sharing this gentle journey through the deepest mystery of all, the simple, extraordinary fact that there is something rather than nothing, and that something tonight is you.